All right, welcome back to Essential Perturbation Theory and Asymptotic Analysis. We're in chapter 3 still, and we'll finish the first slide deck from chapter 3. So far, we've covered the method of integration by parts, Laplace's method or the beginnings of it, and Watson's lemma for Laplace integrals of simple Laplace integrals of the first kind. And now we're talking about Laplace integrals of the second kind, and we'll talk about some modified versions of Watson's lemma. And we'll do some really nice examples in this section. So Laplace integrals of the second kind. So in fact, we gave a definition of the simple version, and the kind that we're going to view over and over again will come in a slightly more generic form that I want to define. I think this is a little bit in way of review because we already covered this slide last time, but it's okay to go through it again. So we're going to be interested in integrals of this form, integral from A to B. A and B could be infinities. Okay, so we could be integrating on an infinite interval. F is some nice function. For now, we'll assume it's continuous. Doesn't have to be. Lambda is going to be our large parameter, and of course, phi is this exponential function for this function e. So this will be an exponential function that will have a particular property. It'll have an isolated single point t naught in AB such that the derivative of t naught is equal to 0, but the second derivative of t naught is less than 0, so it's negative. So what we'll be thinking about is phi function of this form. So here's phi. And t. And around this point, t naught on the interval A to B, t has a local maximum. And then we'll do a Taylor expansion, and we'll keep, we'll just keep up to the second order, replace this by a quadratic. So essentially, this will become a lot like a Laplace integral, simple Laplace integral of the second kind. All right. We talked about this example last time, and so I'll skip this one. And let's go into this example. Suppose that the integral that I'm interested in is the following: integration from minus infinity to infinity of f of t e to the minus lambda t squared. So in this case, we're taking just the simplest possible case. Phi is equal to minus t squared. So of course, the first derivative of phi at the point t equals 0 is 0, and the second derivative is negative. So we're interested in approximating this integral as lambda gets very large. We'll assume some nice things about f, and these things are a lot nicer than actually we need to assume about f. So suppose that f is integrable in the sense that if I integrate the absolute value of f from minus infinity to infinity, I get a finite integral. Okay, some finite number. And I'm going to assume that the following expansion is valid on the interval minus s to s. Suppose that f can be written as its Taylor series expansion. Now, it turns out this is much more than we actually need. We don't need f to be to have a convergent Taylor series expansion. By the way, every time I write something like this, f equals a series that goes all the way up to infinity with an equal sign. That means something very important. It means a few things. So it means that point-wise, this series converges. Okay? It usually means a bit more than that, but at the very least, we're going to say that point-wise, this series converges. That's why we're allowed to write this. And of course, what does it mean for a series to converge? So point-wise, it means that the sequence of partial sums is convergent. It's a convergent sequence. Now, if we have such nice things going on with this function f, and of course f against Gaussian, then if we're only if we only know that f has a series expansion on this modified or the smaller interval minus s to s, you might think we have a problem here. Because what we want to do is put this guy into this equation or this integral and integrate term by term, if that were even possible. Now, the problem here is we're integrating from minus infinity to infinity, but this power series expansion, which is a strong statement that we have a power series expansion, Taylor series expansion, it only works or is valid on the interval minus s to s. So what do? Well, what we do is argue that on the interval minus infinity to minus s, this integral is transcendentally small. We can use some approximations to show that. And I think basically we did that in the previous example, and you can use the same technique. And of course, if that's true, then the integral on the interval s to infinity is also going to be transcendently small. Okay? These are what I call the tails of the integral. So we just need these to be small, and that's why we need this guy to be integrable all the way out to infinity.
Is it just the same step of pulling out exponential and magnifying finite term?
Essentially. So yeah, essentially. It is a little more complicated than that in this case. And if you don't know how to do it, we'll just assume it. Okay. So because making a statement like this does not mean that we're assuming that f is a bounded function, right? It could be unbounded. It just has to be nicely integrable. Now, what we do is we're going to justify this rigorously with a modified version of Watson's lemma. We're just going to throw this integral or this power series expansion into the integral and assume that we can integrate term by term. Now, what we really need to do is we first need to integrate from minus s to s in some sense, right? We throw away these tails of the integral. Then we are integrating s or f times the exponential function from minus s to s. We throw this guy in. We assume that we can integrate term by term. And then what we're going to do is ultimately blow this interval of integration back up from minus s to minus infinity to positive infinity, so that our integral gives us something nice, namely that we get Gaussian integrals. Now we're not going to worry about that yet. We'll tidy this all up in the next theorem. So we're going to assume we can integrate term by term. And we're going to use the fact that this is an even function. Okay, so if we do that, then what happens is the integrations where we're integrating odd monomials against this even function on the interval minus infinity to infinity, well, that's going to be an odd integrand. And so that integral is just going to be 0. So you might ask, where do the powers t to 2k plus 1 go? They vanish because of the fact that the integral or the integrand would be odd in that case. Okay, so we only then have the even parts. And now these integrals can be done exactly. You can just remember they're Gaussian integrals, or you can Gaussian moment integrals, or you can fire up Mathematica and throw it in there, and it never hesitates to compute the right answer when it knows it. In this case, you get the gamma function, gamma k plus a half over lambda k plus a half. All right. And then, of course, we'll stick that back into our power series, and that's our asymptotic series. Now, you know by now that, this is, we've brushed a lot of details under the rug, but this is essentially Laplace's method. Okay, where we adjust these limits of integration, we have a power series that we're going to assume we can integrate term by term, and we just do it as if it can be done without any problem. And of course, this all has to be rigorously justified if you care about those things. If you don't, it's okay because it all works out in the end anyway. But the next theorem is going to justify these calculations. Any questions before we move on to that? Okay, so this is what I'm calling Watson's lemma for integrals of the second kind. I don't know if this is, well, I assume it's not a universally accepted name, never heard of it before. However, some books just call this Watson's lemma. Now, we already had a Watson's lemma for Laplace integrals of the first kind, but if you look in some books, they'll have this listed as Laplace's or Watson's lemma. So, for example, the book that I reference a lot of times for complex analysis is a book by Marsden and Hoffman. And in Marsden and Hoffman, this theorem is called Watson's lemma. Okay, so that's a little bit strange, but I've never seen it called that before. So we're going to call it Watson's lemma for integrals of the second kind. Why not? All right, so here's the statement. Suppose that f is a C infinity function. And I'm going to generalize all this momentarily, but we'll take the simplest form, one that doesn't require us too much pain to do. So suppose that f is a C infinity function from this interval minus t to t into the complex number. So this is it's a function that's defined on the real line, and it has its values in the complex numbers. So I can really think about this if you like. I could write f of t as being equal to f1 of t plus I, the imaginary unit, f2 of t. That's how you can think about this function. Okay, it takes values from the interval minus t to t and converts those to complex numbers. But each one of these constituent functions, this is the real part, this is the imaginary part, are C infinity functions. Okay, let me clean things up a bit. Okay, so that's our assumption about f. Then the integral that we're interested in is integral minus t to positive t, f of t e to the minus lambda t squared dt. And we're interested in this integral as lambda gets larger. And we're going to apply our usual tricks, but now we're going to do so rigorously. This integral turns out is finite for each lambda greater than 0, and the integral is asymptotic to this power series expansion, to this asymptotic series. And notice once again, this is not very likely going to be a convergent asymptotic series, because this guy on the top is going to dominate for values of lambda which are modestly large. So how do we calculate this? How do we calculate this expansion? Well, I showed you or how do we prove this expansion, I guess. So we proved, or we did a very quick calculation in the previous example how this works, and now we want to rigorously justify the steps. So we know what to do whenever we want to prove that a power series is asymptotic. We have to take the last term in the power series associated to the asymptotic sequence and do something with that. Show that it's a little o, or all the rest is little o of that element. Okay, so we'll go through all those steps in gory detail. So the finiteness of the integral I'm going to leave to use an exercise. It's not a hard one. So the first thing you might want to know is that for every lambda, this guy is not blowing up to infinity. It's something finite, a real number. So I'll leave that part to you. Again, we're going to first be interested in the tails. Now, you might say to yourself, there are no tails here, right? But what I'm going to do is I'm going to increase the size of this integral in some way that's going to actually capture some tails. What I'm going to do is replace this f with its Taylor series, finite Taylor series expansion up to a certain point, and then I'm going to expand the interval of integration. So you see, when you do that, we're going to be integrating powers of t against e. And I'm going to want to expand the interval of integration. I'm going to want to know that what I'm adding in, I have to add something in to get an infinite integral, are these tails, or tails of these form. Okay, minus infinity to minus t of t to the 2k e to the minus lambda t squared. Why didn't I put the odd powers in there? The reason is because the odd powers are going to vanish again. So I need to know that this guy is well controlled. In fact, these tails turn out to be TST again. Now this is a little bit different. We have to show this in a slightly different way. The problem here is that this is growing, right? And this is decaying rapidly. The whole thing, however, is still decaying quite rapidly, exponentially slowly, or exponentially rapidly, so that the tails still are TST. But I'm going to leave those arguments also for you guys. Now, again, we're going to be replacing a Taylor series, a finite Taylor expansion for f, or in other words, f for its finite Taylor expansion. And then we're going to increase the size of the integration interval, as I said. So we're going to need to know what the values of these are. But again, we tabulated those from earlier. So as long as k is any positive number or positive integer, actually non-negative, so 0, 1, 2, 3, doesn't matter, this integral is going to be finite and it's going to have some nice values. In fact, you can rewrite all of these in terms of things that involve like square root of 2 and pi, etc. I'm not going to worry about that. I'm just going to write them as the gamma function. So for example, if I put in k equals 3, so 3 plus a half, you can find out that this turns out to be something in terms of pi, square root of pi, square root of 2, and some other terms. It's easier just to bottle it up like that. Okay, so what this means is then if I integrate these guys, monomials against these Gaussians, over this finite interval minus t to t, then the difference between this value, this finite integral over the finite interval minus t to t, is exactly equal to this plus some TST term. So the difference between this and this value that you would get if you integrate over minus infinity to infinity is transcendently small. Okay? And of course, the integrals of the odd monomials against the Gaussians are just going to be 0, right? Because if this is an odd monomial, that's an odd function times an even function integrated over balanced negative and positive sections of the interval are just going to yield 0, right? Now, if this were an integral over minus 5 to 10, then this is not going to be true. But since it's minus t to t, we're fine. Now, if your initial integral was, I should point this out, if your initial integral was from minus 5 to 10, the result's still going to be exactly the same. And the reason is because what we would do is drop this guy and change it to a 5 and argue that what we're dropping is TST. So our arguments end up working out anyway. So sometimes you get the right answer for the wrong reason. Okay, so be careful about that, unless you're not worried about it. If you always fail up or make mistakes in the right direction, then good for you. Okay. Not all of us are that lucky.
Just have one very technical question.
Okay.
So I remember even for odd function, there's one way that we can consider integral as osmotic six of x. Is it called like the Cauchy principal value?
I think I know what you're saying, and I think that's right.
I think Cauchy principal value allow you to define something that is infinite to be finite, right?
I've forgotten the precise definition, but that may be true.
Oh,
Yeah. But in any case, the question is about the finiteness of the integrals, and we're interested in only finite cases to start with. So we'll commonly comment on that and check it. Sometimes I'll forget and just assume that it's finite to begin with. But strictly speaking, you should start out by saying something about whether or not the integral is finite for your range of lambda or not. Okay, so again, this integral on the finite interval minus t to t differs by this this thing by an amount which is just TST. And the odd integrals just vanish. Now here's where we get into the to the details. So what I want to say about f is the following. If I say that f is a C infinity function, f is C infinity minus t to t into the reals or complex, doesn't really matter. Does that mean that it has a convergent Taylor series expansion? Can I write f as its Taylor series? This is a good question for an analyst. Is it true that I could write this as its Taylor series expansion? Yes or no?
For real, yes. For complex, no.
Well, even real case, I can come up with an example where I can't write this as Taylor series expansion. So the answer is no. So if f is a C infinity function, it may or may not have a convergent Taylor series expansion. There's a classical example that we use, and that's called the mollifier function. There's a function out there in the universe which is kind of nice and also kind of pathological. So that function, we can rig it up so that it has the following property. It's 0 all for every value of x negative, and it's 0 at x equals 0. And then it has the nice property that the function and all of its derivatives are 0 at 0. We call such a function a mollifier function. So we say this function has, you may have also heard of this function as a compactly supported C infinity function. All of its derivatives of every order that you're interested in at 0 are equal to 0. Yet this is a C infinity function. It's a C infinity function, no problem, for all derivatives. All right, now think about doing a Taylor series expansion about the point 0. What would you get? Well, if you do the Taylor series expansion and you believe that it converges, you would say, well, that f of t is equal to its Taylor series expansion, k equals 0 to infinity, fk 0 over k factorial tk. Well, what is that sum? It's 0. So you're saying that the function's 0 everywhere. Okay, which is not true. It's 0 over here, sure. But in here, it's not 0. So what's going on? Well, I can't say that it's equal to its Taylor series expansion at the point with the expansion point 0. It's not possible. So, all right, so see, even if a function is C infinity, I can't necessarily say that it's equal to its power series expansion. However, Taylor's theorem still works. Taylor's theorem with a remainder still works. I can expand up to any order, n, 500, 1,000, and I can still say that f is equal to its finite Taylor series expansion plus a remainder term. That's still valid, check. I just can't say that as I take n larger and larger that this guy becomes vanishingly small in some case, in some sense. Does everyone understand that? It's a technical detail. So I cannot even saying that f is a C infinity function, which I've assumed, I can't replace f by its Taylor series, infinite Taylor series expansion. It may not have one. However, I can still do Taylor's theorem, and that's a subtle but interesting point. I'm never going to ask you to prove that in any setting. I'm not, if we meet on the street, I'm not going to ask you to repeat this fact. But it is an interesting fact that if you're interested in mathematics, you should know about. Taylor's theorem, in this sense, always holds, and it holds for any n because I have a C infinity function. So I can expand up to finite orders to any degree I want. This is always a polynomial, of course, and this is the remainder. So the remainder term, remember Taylor's theorem, and this is contained in the appendix of the lecture notes if you have a copy of those, or if you have Google in front of you, or have Google available to you, you can find out that the Taylor remainder in the differential form is just this. There's also an integral remainder of Taylor, which is easy to prove using the technique of integration by parts. But in any case, we can estimate the size of this guy term by term, or for any n, in other words. So if I take the absolute value, I can replace this by its largest value on the interval minus t to t. Now, of course, that constant that you get when I replace that by its largest value is a finite constant, but it depends on n. Okay, so this value here depends on n. That's fine, no problem. When I take the absolute value of the rest of this, remember, I'm in the interval t equals, or t from minus capital T to plus capital T. So when I take the absolute value, I'm going to bring the absolute value in on this guy. And so the monomial is now the absolute value of t to the n plus 1 power. And of course, this is just a constant 2, which I can lump together with this guy. All right, now suppose that n is equal to 2m. I actually have to take this in cases, but the odd case is actually oddly the same. You'll see why. So what we're going to do is we're going to replace this f with its Taylor series, finite Taylor series, up to order n, where n is equal to 2m. Okay, so let's do that. Of course, when we do a finite series replacement for f, we can integrate that term by term because we can interchange a summation, a finite sum, and an integral. And so when I replace this by its first part here, this guy, interchanging the integration and the sum, I just get this. So these are the integrals that basically we've already tabulated. Now we know that the odd ones are going to be 0 whenever k is odd. And whenever k is even, we're going to show, we already know that these are nice Gaussian integrals, right? Given to us by gamma function, et cetera, et cetera. All right, now we argue that the odd ones go away. And so whenever we do this sum, we're summing from k equals 0 to m over f 2k derivative evaluated at 0, 2k factorial in the basement, integral from minus t to t, t little t 2k power, e to the minus lambda t squared dt. So the odd integrals go away. And of course, we keep this integral of the remainder. We can't remove this piece here. Let's see. We can't remove this part of the piece, I should say, because even though that looks like a constant, it actually depends on t. All right, so I can't do a full simplification there, or the simplification maybe to the degree you want. Now here, little n is 2m, so I have 2m here. Gotten rid of the odd powers, and so looks like I'm good. Now, similarly, if n is equal to 2m plus 1, so this is an odd n, because all of the odd integrals vanish, namely even the one of order n, okay? That means that when I do this sum, when I replace this by its Taylor series, I still get exactly the same sum that appears for the first term. These two are the same. That's because the last odd integral actually vanishes. But the remainders are different, right? So this remainder here is 2m plus 1. This one becomes 2m plus 2. Okay, you may have to think about that or write it down, but that's the case. Now notice that what I have is this integral. I can throw that, or sorry, this sum, I could throw it over with I to the lambda. I of lambda, right? And I can do the same thing here. And what that says is actually these two remainder terms have to be exactly the same. Isn't that interesting? The two remainder terms are exactly the same, even though technically they look a lot different. So the two remainder terms have to be the same. That really doesn't matter to us from a certain point of view. The remainder terms are the same, big deal. But in some cases, it is a big deal because then you can use whichever one is more advantageous to do analysis on to get the result you want. It turns out for us, we want to use the smaller to show what we want. Although the larger will work as well for our results. Sometimes, though, and I can imagine a certain scenario where I really do need to use the smaller indexed remainder to get the result I want. In any case, let's define mk, script mk, calligraphic m, to be this maximum. Okay, so does that guy exist and is it finite? Yeah, it exists and it's finite because f is a c infinity function over the closed interval minus t to t. So every derivative of any order over the closed interval minus t to t is a continuous function. Whenever I take the absolute values of a continuous function, I get another continuous function. So the one thing we know about continuous functions is that they always achieve their max and their min, right? So that's another analysis point that I can really be assured that this maximum exists. I'm not taking the maximum of something which is infinitely large. Now, what we want to do is estimate the size of the remainder. Because remember the technique of showing something's asymptotic, we have to show that the error is little o of something. So let's estimate this guy carefully. If we do that, then we can bring this constant out with order script m, calligraphic m to the order 2m plus 1 over 2m plus 1 factorial. And we're going to be integrating then minus t to t this guy. All right, now we can just double the size of this. So we can't just throw away this guy if it's odd. Okay, so keep that in mind. You can't just throw this away. Why? Because the whole integrand is now even because we've taken absolute value, right? We can only argue that the integrand was odd whenever we had t to this odd power times an even function. This guy, Gaussians are clearly even when they're centered at 0, right? And so what we're going to do is just double the size of this guy, double the size of the integral, from 0 to infinity. And then we use the fact now that when we're on the positive side of the real axis, the absolute value can go away, right? Why can we double the size of the same integral on the interval 0 to infinity? It's because the integrand is even, right? So integrating on either side just gives the same value. So twice integral from 0 to infinity, and we can replace the absolute value with the regular thing. And this guy is a tabulated integral as well. It's got a finite value. If you plug that into Mathematica, you'll see it comes out as gamma to the m plus 1 over lambda to the m plus 1. Okay, now the important point here is not all this stuff. Well, it is important. This constant that remains can depend on m, no problem. But this guy here is what we're interested in because it's this that we're going to use to show the little o-ness of that term. Now, what we need to show is essentially the remainder integral is little o of the last element of the sequence which appears in the sum up to that point, which turns out to be lambda to the m plus a half. How do I know? Because when I integrate this, I should get a lambda to the m plus a half. Okay. And how I know that is because I should have written it there earlier, but that's because of this calculation. So it's going to be lambda m plus a half, the last sequential, the last element of the asymptotic sequence appearing in the asymptotic series. Okay. Is this guy. So I need to show that this is little o of that. And since m is going to be arbitrary, or already is arbitrary, that'll prove that I have an asymptotic sequence. Now, clearly it is, because if I use my standard trick and show that when I multiply by lambda m plus a half to the remainder integral, okay, if I multiply this guy by lambda to the m plus a half, then which guy is going to win at infinity? The one in the basement wins. And so that integral, or that limit, is going to go to 0. We use the squeeze theorem to show that that means that this guy has to go to 0. Remember that process? And that means that the integral remainder, the integral of the remainder, is at least little o of lambda m plus a half. Now, what could I have said about this guy? Well, this guy here, lambda m plus 1, anything which was smaller than m plus 1 will work, or any lambda to any power which is smaller, right? So if it had come out to be a quarter, I would have been fine. If it had come out to be 3/4, I would have been fine. Actually, if it would have come out to be lambda to the m plus 9/10, I would have been fine, right? Because I still have a little bit of room. Here it's lambda to the m plus a half power. And so this guy wins at infinity. That means the limit as lambda goes to infinity is 0. And that's what we need for little o-ness. Okay, so what we've actually shown then is putting everything together. I skipped a little step in there because we have this transcendentally small term that we have to take care of. But that's not a big deal, because we know that if we have an expansion for of something, then if we have the same expansion which has a correction of only transcendentally small terms, then the expansions are going to be the same. Okay, so that was a theorem that we proved earlier. So I minus this is little o of that. That's the last term. See, notice the last term that appears here is going to be lambda to the m plus a half. So that's why I needed o of 1 over lambda to the m plus a half. And so the asymptotic sequence that we wrote down is correct. Any questions about that? Excellent. Okay. Now, we can make any number of corollaries to this. And I promised you, I'm not going to get bogged down. You probably, some of you probably think I've already been bogged down in proofs. But proofs for us are proofs by calculation. We're just doing calculations. It's never more detailed than taking limits and doing integrations so far for us, okay? It's never more than that. And of course, we're here interested in TST terms sometimes and so on. Here, I really am going to do a hand-waving proof for this one. I'm going to modify my assumptions a little bit, and you can see probably from looking at the previous proof how you could modify what I'm about to say and make it completely rigorous. So you could fix up the argument so that everything is completely rigorous, and so but we're not going to worry about that now. We're going to do sort of a hand-wavy non-rigorous proof. But here's how I'm going to modify things. I'm going to assume that f can be written as absolute value of t to the sigma power times g of t, where g is c infinity on a interval minus s to s, which can be smaller, or has to be actually smaller than minus t to t. Notice that this guy could possibly blow up. I just need sigma to be greater than 1. So if sigma is like sigma is greater than minus 1. So if sigma is minus a half, that works. But this guy this part here is going to blow up, right? It gets large at t equals 0, but that's fine. All I care about is that f is integrable. It has a finite integral. It's the product, however, something that blows up times something which is C infinity smooth. Now remember, just because I assume that this is C infinity doesn't mean it has a power series expansion again. It doesn't necessarily, but we're going to pretend that it does in the same way that we know that Taylor's theorem is going to work, and usually that means that we can do our asymptotic asymptotic series analysis without any problem. So we're just going to pretend that this really does have a infinite series expansion and integrate that sucker term by term and not worry about it because we're all friends, right? Okay, so if all of this holds, then the integral that we're interested in, this one, is finite for all lambda, so that's good. And it has this asymptotic expansion. So the only difference here between that and the last one is, and you can see this, if I set sigma equals to 0, then I really do get the last theorem where this is just f itself, right? And so notice that in that case, this would just be f, and sigma is equal to 0, means that goes away, and this is exactly the result of the last theorem. So all we're going to do now is pretend that f can be written as a convergent power series. So this is wrong. This is not an actual proof. So health warning, okay? That's why I wrote proof sketch. This isn't a proof, this is a proof sketch. This is essentially what you're doing, but it doesn't really work rigorously. And I hate to keep bringing it up, but I know some of you just don't care about that, and that's fine. This is a Big Tent course, and all are welcome. Okay, so this is not necessarily true, but we're going to pretend it's true, and we'll get the right answer. Now, we have this integral that we want to calculate, right? And we're going to pretend like the power series expansion is valid, and we're going to throw it in. But when we do that, we're going to make an error, right? We can only use that power series expansion on the reduced interval minus s to s. And so we have to cut off the tails. And when we do that cutting off of the tails, then we have to replace this with an asymptotic symbol. Okay, again, this is my hand wavy version of this. This is essentially the method that Laplace came up with, and the rigor was added later by Watson and others. So now I also assume that I can integrate term by term without any penalty on the interval minus s to s where the integral is valid, or where the expansion is valid. Then I do another squiggle, because what I'm going to do is add back transcendentally small terms by expanding my interval of integration from minus infinity to infinity. Okay, but no problem again, because I'm only adding back transcendentally small errors. And now I can integrate this guy term by term. The odd powers go away. They go away because the integrand will end up being odd. Actually, let's see, am I right about that? So what have I? No, let's see. Yes, yeah. Okay. So why it looks at first like I might not be right, right? But I am. So the odd integrals are going to go away because this guy is going to force it to be odd. This one here is an even function, and this guy is an even function. So if I multiply an even function, and the product of two even functions is even, you guys remember that? But if I multiply that product of even functions times an odd monomial, that makes the whole integrand odd. And I'm integrating over balanced intervals, and so the odd ones go away, only the even ones remain. And then I'm going to do the trick where I replace this guy or this integral by the integral from 0 to infinity and double the size of it, because what I have left is an even thing. Then I can drop the absolute values, throw that into Mathematica, and Mathematica says I'm happy, and it returns that. Okay, so it gives you the answer that you want. So again, this is Laplace's method. I pretend I can integrate term by term. Even if I change the interval of integration from something larger to something smaller, no problem. I'm only making errors which are transcendentally small. Then I can increase my interval back to the larger domain of integration, again arguing that I only make transcendently small errors, and assume that you can do all the while do the term by term integration. Okay, in other words, I can replace the summation and the integral. You can't always do that, right? If I were to prove this rigorously in an analysis setting, I would really need to know that the power series converges uniformly in order to replace the summation and or interchange the summation and the integration. But I can't do that in general. Okay, I don't even have remember, I don't even have a convergent power series expansion necessarily. Questions about that?
Did you drop a 2 in the last step? I can't remember how the
Yeah, so I added a 2 to convert this to 2 times 0 to infinity. And then when you integrate that, you get a 2 back, or a half back, and then they cancel. So in the book, I didn't skip the step, but in the slides, it was unpleasant to have one extra line in the calculation. So that's one thing I'll say that's sort of universally true. The book tends to have more details than the slides in a good way and in a bad way too, I guess. It's a little more sentences and paragraphs that students like to overlook as opposed to just calculations. But there are some really good things in there too. Once again, I want to please ask you all to read the notes and look out for typos. Some of you have been really good about showing me my typos, and I appreciate that. That helps make the slides better and the notes better. So before I move on to some really fun examples, so in way of an announcement, so these slides were fresh or hot off the presses 10 minutes before class. So if you haven't gotten, if you're looking at something and it doesn't look like the right set of slides, then that's because I always update them right before class. That's why I discourage you from printing them out too, because they constantly change. So go grab the slides, and I also posted the lecture notes on Canvas right before class as well, so that there's a fresh copy there. Again, probably shouldn't make printed copies of that either, because it changes so frequently. All right, let's do a fun calculation, a couple of fun calculations. So I want to calculate or approximate this Laplace integral as lambda gets large. So we have to identify everything in sight, right? Or it's at least useful to do so. So our phi function in this case is going to be minus the cosh. So phi is equal to minus cosh t. This is an even function, right? So cosh, I believe, looks like that. And so minus the cosh is going to look like that, right? Around t equals 0. This is an even function, right? And so there's no prefactor out in front, f of t. And so I can easily just shift this integral. I don't have to worry about whether it's an even or odd function, multiplying it out front. There's no monomials or anything like that. So let's shift this to be an integral over the interval 0 to infinity and add a 2. Okay. So here, this should say minus cosh t, I believe. So the derivative of cosh t or minus cosh t is 0 at t equals 0. And of course, it's a frowny face, which is what we want, right? It's negative second derivative. So it looks like we can apply our methods. Now notice that what we have is the following. So minus lambda cosh t. This is basically this negative quadratic times lambda. So the idea here is that if I just took what appears in the exponent and replaced it by that little Taylor expansion up to second order, then it approximates it pretty well, especially as lambda gets larger and larger, right? Because for what reason? So as lambda gets larger and larger, essentially this guy is becoming more and more like a Gaussian. Okay, it turns out it's becoming more and more like a Gaussian, and this is a perfectly good Gaussian candidate. So that's kind of the argument of why that's happening. But we don't, if you just put this approximation in right here and do the integral, you get an asymptotic approximation, but not a full asymptotic approximation, only to one term. So if we want to get more, then we have to do more. So what we're going to do is kind of inspired by that. We want to do a replacement, which looks basically like this, with a new variable. So if I replace this with a variable tau, I can replace this by equals and then solve for that tau if possible. So that's exactly what I'm going to do. Again, we're interested in the interval where t is positive. So I'm going to introduce a change of variable. Tau equals cosh t minus 1. Okay, cosh t minus 1. Cosh t is positive, no problem there. In fact, it's greater than or equal to 1. So if I subtract 1 from it, that's still a number which is greater than or equal to 0. I can take the square root, okay? You ought to always be worried, at least if you're not worried about rigor in all cases, at least be worried about whether you're taking the square root of a negative number, okay? Now, square roots of negative numbers are fine in this course when we start talking more about complex numbers and complex integrals, but you should be more careful here when we expect it to be real. All right, so now in either case, I can replace this tau with, I could rewrite this as, this is if and only if sort of, 1 plus tau squared is equal to the cosh. Right? So that's essentially the replacement that I'm going to get out of all that. I'm going to essentially replace cosh t with 1 plus tau squared. All right, so let's see. Okay, so I'm neglecting the half too, because is that fair? Yeah, I can define tau to be whatever I want. Okay, so I've kind of absorbed the half in here with this definition, if you want to think about it like that. All right, all that matters is that I'm redefining this as something which is a simpler quadratic. All right, now what I want is to find I want to replace dt with something d tau, right? So let's implicitly take the derivative of this guy here and see what we get. Actually, which one am I doing first? D by d2. I think I'm doing an implicit differentiation here, but I can't, yeah. Okay, so take the derivative of both sides of this guy, right? With respect to t. And then pretend that tau dt is just a fraction, and then solve for dt. So that's where you get this. Now, the sinh, that can be written as the square root of cosh minus 1, a little trigonometric or hyperbolic trigonometric in a equality or identity. Okay, so I'm going to write the sinh as being, and remember also that the derivative of the cosh is related to sinh. So what is the derivative of the cosh?
Sinh.
Just sinh, right?
No
So,
negative.
no negative sign, right? And of course, we could remember all this if we don't have to remember it. Mathematica does. That's fine. But you can always rederive some of these things by saying cosh of t is, this is one of the only ones I remember. It's e to the e to the t plus e to the minus t over 2. And the sinh, what was that? Sinh is e to the minus t,
And then EP minus.
or sorry, yeah, plus minus e to the minus t over 2. Okay. All right, so in any case, I think this is correct. And you can prove trigonometric identities, right? If I square these guys and add them up. So I get this, but I have a replacement for this. This is just equal to 1 plus tau squared. So you square this out, right? That's from here. I get, when I take this out and subtract off the 1, this is 2t squared, or tau squared plus tau to the 4th. Now I can pull out a factor of tau squared out of the square root. That cancels with this. Remember, tau and t are both positive, so I don't have to worry about that. Comes out without the absolute value. Cancels with this, and I can bring out also a square root of 2. And that's going to cancel with one of the 2's, or one of the square roots of 2 up on top, and so I ultimately get this. So notice that even without knowing how to write t explicitly in terms of tau, I can get my dt using a trigonometric identity. Nice little trick. So now when I convert this integral, I have this to start with, and it converts as that. Okay, so there's e to the minus lambda. Where did that come from? It came from the replacement of cosh is equal to 1 plus tau squared. Okay, so one of those guys came out as e to the minus lambda. Now, what about this guy here? I can treat that now as my f, and then I can go back to my Watson's lemma for integrals of the second kind. So this expansion, or this function, f of t, or f of tau, sorry, square root 1 plus 1/2 tau squared. So we can use a binomial expansion for that. And if you don't know what the binomial expansion is, you should have a look. Go to Google, look it up. It's a very useful expansion for asymptotic calculations. In fact, the one that we're going to use all the time is 1 plus t to the alpha power. All right, so in this case, alpha is equal to 1/2, or minus, yeah, 1/2 in this case. You can also write it as this, where alpha is a negative power, okay? So here we're writing it where alpha is a positive power. And so then I replace, when I do this expansion, I replace t with 1/2 tau squared. And so that's why I just get even terms. Now, this binomial expansion is only valid for this argument here between -1 and 1, but the argument is already positive, so we can just say the argument has to be, this guy here has to be between 0 and 1, not including 1. Again, the story is this power series expansion isn't valid for the whole interval, for the integral that I'm interested in, but that's okay, because I can add or subtract transcendentally small terms ad nauseum, right? So I can throw that, oh my goodness, skipped a whole lot there. Let's see, where are we? Okay, so I can now throw this guy into here and basically pretend I can do term by term integration, because the theorem says that that's the result of that's the end result of the theorem. It says I can do the term by term integration. But now notice when I do the term by term integration, I don't get this is equal, right? In some sort of convergent power series sense, it's equal to an asymptotic series, or it's asymptotic to this series, I should say. In any case, we do these integrations, these Gaussian integrals. I don't know how to do these, but guess who does, right? Mathematica, no problem, starts replacing these guys. And as I said, they're just square roots of pi and things like that. And you can check what the values of those are just as well as I can. But these integrations, these even Gaussians, actually, these are what I would call moment integrals, not exactly Gaussians, but Gaussian moment integrals, are just finite, and Mathematica loves to do this sort of stuff, and so you can throw it in there and it gives you this asymptotic series. We can simplify a bit by pulling out some half powers of lambda, and so I write that as a lambda to the 1/2 or square root of lambda, doesn't matter. And so I can pull out all this. Remember, there's no problem pulling out factors of lambda out of these series. They're not convergent series, they're asymptotic series, and you can do a lot more with asymptotic series than you can with other series. But anyway, in any case, I can pull out these common factors, and this is the expansion that I get. And you don't have to take my word for it, because Mathematica has a asymptotic integrate command. In this one, it doesn't work perfectly. So for this one, I put in the integrand that I want, the interval that I want, and I ask it for a one-term expansion for lambda as lambda is going to infinity. This is the code that you use. And it does what I asked. It returns that one-term asymptotic expansion. But sometimes Mathematica doesn't work. You'll see in the next example that Mathematica actually works and gives us what we want. If instead I ask for 3 terms of an asymptotic expansion, it still says, no, I'm just giving you 1. Enjoy. It gives the same term. Now that is the leading order term that appears here, okay? So it's giving us our first term. It's just saying it doesn't know how to do the 3 term, and it's not giving any kind of error message here. It's just saying, there you go, enjoy. So this happens a lot with Mathematica, and if you decide in your career that you want to just assume Mathematica or some software package is always right, so as time goes on, you're going to be increasingly correct. Packages are going to get better and better, and in 5 years' time, if I put this in there, Mathematica is going to give me the 3 terms that I'm looking for, or 100 terms, I don't know. So Mathematica is going to get smarter, but why is Mathematica getting smarter? Because some programmer is telling it what it should do in order to handle this asymptotic expansion. So that's why you need to know what's working or what's happening under the hood. You need to know these things. Now, I don't think it's a bug. So this is just common with Mathematica. You ask for something and it gives you as many terms as it can, but it doesn't say why it can't deliver more. But I don't know if I would consider this a bug. It's just pretty typical for Mathematica. Maybe you could consider it a bug in the following sense. It should at least say, I can't do better, but here's 1 term. Okay.
Just like having a surrender.
Yeah, exactly. Mathematica is waving the white flag. And the next example, I'm going to use our techniques to derive an approximation for the gamma function. So this is Stirling's approximation. And we've already done this in a very crude way. Now I want to do this in a bit more detail. So this is the last example, but you can see that it's a fairly long one, and it's going to require 7 or 8 slides to do. Are there any questions before I get started? I did want to say the homework is due Thursday, right? But if you need an extension, you can email me or speak to me in person, ask for an extension, no problem there. And the homework should be typed in LaTeX, as I said. If you have a good reason why you can't deliver the LaTeX by Thursday, you can always ask for an extension, no problem there. I'm happy to grant extensions for good reasons. And but I'm expecting the homework to be turned in LaTeX unless you talk to me beforehand and get a dispensation of grace, right? Forgiveness, not forgiveness, but a dispensation of grace. All right, so let's talk about the gamma function and Stirling's approximation thereof. So this is the definition of the gamma function, and it doesn't look like an integral that we can attack. The lambda is not even inside of or in a power of, or in the exponent of the exponential function, right? But it's not hard to make it so. We can use the following very simple argument. At least for t positive, we can say t to the lambda is the same as e to the lambda log t. Okay? No problem there. So we can substitute this in. We could combine these two terms, right, into one exponential by adding. But there's still no point t naught such that I can find phi of, actually, let's see, did I get this right? Oh, this one does not depend on lambda. Okay, so that would be treated right now as our f function, right? And this would be our e to the something. So this would be our version of phi. But the problem is phi is the log of t, and this doesn't have a derivative which is 0 at any point, right? So log carries on its merry way like that, never turns back down. Okay, so this doesn't look good, but we can do a another change of variable. Or did we do a change? No, we didn't really do a change of variable yet. We can do a change of variable. All right, so I claim that if you do this change of variable, s equals t over lambda, then it's clear that dt is equal to lambda ds. Then I can get the following integral out. So there's a little trick to showing why that's true. But if this is true, then the integrand that's what we're interested in, looks like this now. Now in this case, again, we don't have to worry about this because this does not depend on t. We're really only interested in what's happening in the integral, in the integrand. So now we can say, well, okay, in this case now f is just back to being 1. And our phi is then going to be minus s plus log. Actually, yeah. So this is another typo here. This should be with a minus sign, minus s plus log s. Okay. All right, minus s plus log s. This guy actually does have a derivative that is equal to 0. So if you look at that function, minus s plus log s, then let's see, I think it actually looks like that, something like that. So here at 1, we have a derivative of our function phi, which is equal to 0. And the second derivative is a nice frowny face, right? It's negative at that point. So we're good to go there. So what we can say then is that we could replace this by its quadratic function here, right? Quadratic approximation, just the Taylor series or the Taylor polynomial of degree 2 at s equals 1, right? That would be something like saying, let's replace this with that. And then we could say, well, then the exponential would be like that. That would give us a one-term approximation if we do that. But we want more. We're greedy, right? So what do? We do what we did last time and say, okay, well, if I have an approximation like this, then I can maybe replace this with an equality with a quadratic term, like tau squared. Before I do that, I want to get that Laplace max point, which is here. I'm going to shift it so that it's back here at 0, right? So let's do that. If I do the shift, another change of variable, see, we were in S, right? So let's go back to T. T equals, that's kind of that's abusive, right? So, but let's go back to T and say T is equal to S minus 1, T equals ds, and so I can shift it back to an integral which looks like that. Now, what do you suppose we're going to end up doing? Well, this is an unbalanced interval, but I'm probably going to just chop that off and make it a 1, right? Balance the interval, replaced by a convergent or a power series expansion, which I hope is convergent in some regime. Argue that I'm just killing off transcendentally small terms, blah, 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 right? So I'm not worried about the fact that this is an unbalanced interval, okay, at least not yet. But now we want to do what we did previously. I'm going to say tau or something like it. Tau is equal to square root of t minus log of t plus 1 for only for the t greater than 0 portion, because you know, in the end I can neglect this -1 and I can even things out in the end. But this is the same as 1 plus tau squared is equal to t plus 1 minus log of t plus 1, which is all of this business here. Okay, so in essence, what I'm doing is replacing what is really ugly there by something which is going to be quadratic and I can deal with using the Watson's lemma or Laplace's method, however you want to look at it. Here's the trouble, though. I really, when I go to find my conversion for, let's say, dt and everything else, I really need tau as a function. Well, I need t as a function of tau first, and then I need the other way around. So what I really need is, I really need to say, what do we need in the end? We're going to seek to write t as a function of tau, which isn't necessarily easy when we look at it this way, right? Here we'll cancel the ones, no problem there. Right, so what we need then is a way to invert this power series. So what we're going to do is replace this guy, log t plus 1, by its power series. That's well known and pretty simple, actually. So actually, after we do cancellations, we're going to start off with the sum k equals 2 to infinity minus 1 to the k over k, t to the k. And this power series expansion is valid for minus t between -1 and 1. Now that seems like a problem for us, but again, it's not a problem because we'll just throw away everything that doesn't quite fit the model. But what we really need is t as a function of tau. How do you do that? Well, has anyone ever heard of inverting power series before? So Mathematica knows how to do this really well. But if you didn't know Mathematica knew how to do it, I can show you how, or what it's doing at least. So we're interested in an expansion of this form, but we don't know the coefficients A. How do we figure them out? Well, we have this power series expansion from here. So if we know a power series expansion for t, we just substitute it in and start expanding to our heart's content. Now you have to expand infinite series, and that's not easy, but at least you can do it recursively and without too much trouble. So what we have to do, we have to plug in this power series expansion for every t. Of course, t comes in powers of 2 and 3 and 4, all powers greater than or equal to 2. Then we expand this guy out and we equate powers of tau. So there's only one power of tau over here, but we can say this is really 0 tau plus 1 tau squared plus 0 tau cubed plus 0 tau to the fourth, etc., all the way up to infinity. And this guy has a bunch of different powers of tau, all starting with tau equals power 2, right? Tau to the power 2. So what we get when we start doing that expansion, I've shown you how to expand power series before. You get 1 is equal to 1/2 a1 squared, so I can figure out what a1 is going to be. It's square root of 2. And then the next equation that I get when I do my expansion tells me what a2 has to be, and a3, and so forth. Now, who's really good at doing something like this? Mathematica. If you say, here's my tau squared in terms of a power series involving t, it'll tell you what t is in terms of a power series for tau. So you get all this business. So that tells you what dt is, right? So we have now t in terms of tau, so we can compute dt exactly, and we can do the replacement. So what do we get when we do the replacement? We get t gets replaced with d tau and then a power series. But what do we know how to handle pretty well with our methods? Integration of Gaussians against terms from a power series. So you plop that into your integral. Assume you can do integration you can do term-by-term integration ad nauseum. This one looks like it's only in, so this one has even and odd powers, right? But the odds are going to go away. We'll balance our interval, even though we're not on a balanced interval to begin with. We're on -1 to infinity, but we're going to balance that. And we can integrate term by term by balancing over -infinity to infinity. And of course, those are just Gaussian tabulated integrals. We get them here. And finally, we can do some simplification, pull out common factors, and we get this. And this is Stirling's approximation. In fact, what Stirling had was, I think, either just this one and this one. And remember, Stirling wasn't the first person to come up with this this expansion in the first place, but he did fill in a couple of the terms. He nailed them down. Now, at least Mathematica can do this one pretty well. So if you put it in Mathematica and you say, I want the asymptotic expansion of the integral t to the lambda e to the minus t, you can just put it in there as the Gaussian. You don't have to even refine it. So apparently it just knows this one. So some coder worked hard to put all the guts in to make this one work, because this one to me seems much harder than the previous one we put in. You ask for the integral over the interval 0 to infinity. And lambda, the power series expansion, asymptotic series expansion, lambda going to infinity, and we want 3 terms. So if you ask for that, then you get this. And after some simplification, it agrees with what we had. Okay. Wow, felt like I really talked fast there at the end, but I think I only abused your patience by taking 1 extra minute of your time. Are there any questions before we sign off for the day? Well, if you do have a question, you can always come out afterwards. You can ask in chat, but I'm going to sign off for now, and I'll see you guys on Thursday. Have a good one.